Guys, in today's video we're going to be talking about ionization energy. So at the end of this we should be able to define what ionization energy is, look at its trend, predict ionization energy, especially with successive electron loss, and then determine what happens if we're trying to lose or remove a core electron, and then recognize where there might be irregularities within ionization energy. So let's start with our definition of ionization energy, and this is the minimum energy required, so it must be inputted, so to be inputted, in order to remove an electron from a gaseous atom or ion. Okay, it must be gaseous, and it can be an atom or an ion. And then, of course, the energy is going to depend on what electron you're removing. So our ionization energy depends, so IE is just ionization energy, depends on the type of electron you are trying to remove. Is this a core electron? Or is it a valence electron? A valence electron is going to have a lot less energy required to remove it. Are we removing an electron from an atom or an ion? It's easier to move an electron from an atom than it is to remove an electron from an ion. Okay, we have our first ionization energy, IE1. And this is going to be that electron from an atom. So electron moved from an atom. So it's going to be from a neutral species. Then our second ionization energy, this is going to be removing an electron from a +1 ion. A little bit harder. The more electrons you remove from the same species, the harder it is, the more the energy is to remove that. And we can see that if we look down at this table. So here are our first ionization energy, second ionization energy, third, fourth, fifth, so on and so forth. And we can see as we go from our first to our second to our third, and so on and so forth, the energy is always going to increase as you remove an additional electron from the same thing. So removing that first electron will always be the easiest, and then each successive electron will require more and more energy. Now, you might notice this little stair step right here. This stair step is the in-between valence electrons and core electrons. So all the electrons in white are all electrons that the ones that are being removed are all valence electrons. Once you go from a valence to a core electron, that energy increases significantly. It's much harder to remove a core electron versus a valence electron. So much harder to remove a core electron versus a valence electron. Requires a lot more energy. And that's why our core electrons usually don't get messed with, right? They have a significantly larger effective nuclear charge than our valence electrons are going to have because they're a lot closer to the nucleus. They're happy. They don't do any chemistry because they're set. They don't want to do anything. So in general, when you're thinking about your ionization energies, the first one is always going to be the easiest to remove. Any successive one is going to be more energy than the one before it. And then if you are going from a valence electron to a core electron, that increase in energy is going to be exponential. Okay, so let's look at our first ionization energy trends. So the trend here is going to follow along with our effective nuclear charge. As we go across our period, our forced ionization energy is going to increase. So it follows the Z effective as we go across a period. And this is where we're increasing our effective nuclear charge. So Z effective goes up, electrons get pulled in closer to the nucleus. And as we have our electrons being held more tightly, it makes more sense that our ionization energy is going to increase. So the first ionization energy will increase in value, as in it'll be harder to remove an electron. And then going down a group, we're going to decrease in our ionization energy, again following our effective nuclear charge. So going down a group, our first ionization energy goes down. It gets smaller. So it becomes easier to move an electron. Okay. Now, some notes on this next one is now we are getting our electrons further and further away from the nucleus because we're increasing our N value. So increasing N value. Electrons are further from the nucleus. With a smaller Z effective, easier to remove. When we're going across our periodic table, there'll be a greater variation in our S and P blocks in our ionization energy versus our D and F blocks. So our D and F blocks have a more gradual change in I1. Okay, so very, very, very little changes in our D block, even less in our F block. Okay, so let's look at what factors are going to influence our ionization energy. And of course, Z effective is going to have a significant role to play in here. So our ionization energies are very affected by Z effective. Greater Z effective, greater ionization energy. So greater Z effective, greater ionization energies. And you'll see ionization energies as both I1, or I like to write it as IE1 for your first ionization, and then I2 or IE2 for your second ionization, and so on and so forth. So just a subscript with the number tells you which electron you're removing. So we're going to see, we see visually that we are increasing our effective nuclear charge like so. Now, you might be looking at this trend and seeing some irregularities within here, and that's because there are some irregularities. So for instance, if we are going to remove electrons from a subshell which only has one electron, the trend is not always followed. If you remove an electron from a subshell that only has one, the ionization energy is not as large as the trend predicts. Right, we've got this one extra electron in the subshell, and it's a little bit energetically favorable to remove it from that subshell, which is why you see a dip in ionization energy right here. Okay, so a little bit more of a dip in ionization energy. We see beryllium's 899, boron's 801, magnesium is 738, aluminum is 578, stuff like that. So they kind of dip down more than expected because we're talking about now you're removing an electron from a subshell that only has one electron, and by removing that electron, it becomes just a little bit more energetically favorable. Another thing that we sometimes see is if we remove an electron from a subshell that has only one paired electron, and then we go to one where we have all unpaired electrons, that will also have a irregular trend. So if you remove an electron with a subshell that only has one paired electron, one pair of electrons, the rest are unpaired, the trend deviates a bit. So we can see this when we look at between nitrogen and oxygen, phosphorus, sulfur, less so as we keep going down. But with those four, we see that nitrogen and phosphorus, those are half-filled states. And then we add in one more electron in oxygen and sulfur, and now we have a pair. So when we remove that electron to get back to a half-filled state, it's not quite that unfavorable of a process. So you have kind of a dip in the expected trend. So instead of oxygen being greater effective nuclear charge than nitrogen, or sulfur being a greater effective nuclear charge than phosphorus, you actually get a decrease in that value. Okay, and that is everything for this video on ionization energy. I will talk to you guys in the next one.